Hi, Year 10s. A number of you were away today. In class today, we had a bit of a look at pedigree charts. These are not pedigree charts. These are Punnett squares. This is a Punnett square for someone with attached or unattached ears. This is a Punnett square that's X-linked. Punnett squares help us to guess the probability that something might happen. Here we see a Punnett square for someone with unattached or attached ears. Unattached ears are said to be a dominant trait. Attached ears are said to be a recessive trait. In this particular Punnett square, we see a parent that is heterozygous for having the allele for unattached ears and also the allele for attached ears. This is the allele that they will actually demonstrate. Their phenotype for this person will be unattached because that's a dominant allele. This person then has a partner, is crossed with someone who has attached ears. They're attached ears down here. This is a homozygous recessive trait. What the Punnett square tells us is the probability of the children that might result from this union. There is a 25% probability the children will be like this, 25% probability but they'll be like this, 25 and 25. When we look at it, we can say that the probability of a child from this union being an ear-attached child is going to be 25 plus 25, 50%. Because we see we have two boxes here, which are homozygous recessive, and we have two boxes here, which are heterozygous. Heterozygous individuals will demonstrate the trait of unattached ears. Homozygous recessive individuals will demonstrate the trait of attached ears. In our Punnett square, where we see something that is sex-linked, in particular, this trait that we're looking at here is haemophilia. It's a recessive trait and it's attached to the X chromosome. It's attached to the X chromosome. This is interesting to us because of all of the homologous pairs in the human condition. We've got 23 homologous pairs. The 23rd pair are the X and the Y, the sex chromosomes. And they are not identical. They're not similar. The X is quite large. The Y is very, very small. The gene for your blood being able to clot, to make a blockage and therefore stop you from bleeding in the event that you have a cut, that gene is located on the X chromosome. It is not located on the Y chromosome. We say that haemophilia is an X-linked recessive trait. For those individuals who demonstrate, who have the phenome of being a haemophiliac, they have either two X chromosomes, both with the recessive trait, or they are a male, one X chromosome with the recessive trait in that situation there. In this particular Punnett square, we've shown that we have the X and the Y chromosomes. The alleles are placed in the Punnett square as superscripts over those X and Y chromosomes. There is no allele for haemophilia or for good good clotting. There is no allele for this in the Y chromosome, so there is no superscript up here. Again, this Punnett square, all it does is it gives us the probability of a child from a union such as this. In this union, we see this is the male. I know this is the male because we have an X and a Y chromosome. This person is a haemophiliac because their X chromosome has the recessive allele in it. That person is combining with a partner who is a female. I know it's female because we have X and X, and the alleles that they have on display are the dominant good clotting allele and the recessive haemophiliac allele. When we see this combination happening, we see that the possible children that might come out of this union are going to be female haemophiliac, two lowercase h's there. Female, not a haemophiliac, but a carrier of the condition. Not demonstrating the condition, but a carrier of the condition. And we have two males, both of whom have only one X chromosome. This male is going to be a haemophiliac. This male is not a haemophiliac and is also not a carrier of the condition. This male only has one X chromosome. That X chromosome has the dominant good clotting allele. Punnett squares tell us what might happen. Today we were looking at pedigrees and pedigree charts, and they tell us what has happened in a union. We trace pedigree charts going backwards to try and figure out whether a trait is dominant, recessive, whether or not it is X-linked, Y-linked. So they're good for looking at the phenotype of individuals, seeing the phenotypes of individuals, and then from observing these phenotypes going backwards through the generations, we can hopefully track where the alleles have come from. This is a really simple pedigree chart. We have the parents here and the children here. The symbols that we're using in this pedigree chart are as follows. Squares indicate male. That's a male. Circles indicate female. We have a female, we have a female, we have a female. This T-like icon that we see here indicates a union. So these two have come together and they've had two of these females, two daughters, if you like. Shaded sections indicate the trait of interest. We might choose to shade a dominant trait. We might choose to shade a recessive trait. It is not automatic that the shaded boxes indicate a dominant trait. It could be a recessive trait that's being shaded there. The pedigree chart shows us the phenotype of the individuals. We have generation I, the next generation, I, and then of course down here will be a third generation, I. By looking at the phenotypes, by looking at the combinations of these people, we can hopefully determine whether or not this is a dominant trait or not a dominant trait. In this particular example, we are going to say, oh, it's got a thumbs up. In this particular example, we are going to say that the shaded region indicates a dominant trait. It doesn't have to be, but for now, this is going to be a dominant trait. So for the sake of this particular pedigree, I am saying that this is a dominant trait. So we'll say that shaded in this case is going to be dominant. In class today, I used the example of microbrowsia, my imagined genetic trait. I'm going to say that microbrowsia or monobrowsia has only is a dominant trait where capital M indicates it. So if we said that this was a dominant trait here, that would make 1, 2, 3 individuals phenotype the recessive trait of having 2 eyebrows. I'm saying that 1 eyebrow is dominant. That's just make-believe. I'm making it up. And I'm saying for the sake of this pedigree chart that 1, 2, 3 individuals are in the recessive state, recessive phenotype. The only way they can be the recessive phenotype is if they have a particular genome. The genotype of these individuals, therefore, is going to be, so if our individuals are not members of the monobrowsia fraternity, then we are going to say that they have the genotype of lowercase m. That is a homozygous recessive genome. That would mean that the mother is also lowercase. Now, over here, we see the father shaded has monobrowsia. The father shaded has monobrowsia. And so we know that this individual has to have a dominant monobrowsia allele inside of their cellular structure. But they pass onto the daughters a recessive allele. So that tells us that because this particular daughter has to get a lowercase m from the mother and a lowercase m from the father, this tells us that the father cannot be homozygous dominant. The father has to be heterozygous. That's a very simple pedigree chart. Let's try something a little bit more interesting. Okay, so I've put together a pedigree chart for ears. In this particular case, we are going to say that ears have alleles capital E and lowercase e. Capital E is unattached, it is dominant, lowercase e is attached, that is recessive. I'm going to say for the sake of this pedigree chart that shaded individuals have phenotype attached ears. So straight away, because I know that the shaded individuals have phenotype attached ears, that tells me that they have to have genotype lower E, lower E. We'll put that one in. Okay, with that knowledge, this female, this male, they had 1, 2, 3, 4 children. So let's go through and just talk about who we've got here. We've got ourselves, I guess you would say, the grandparents up here. Down here, we've got the grandkids. We've got generation 2 through there. Let's see who they are. We've got a grandmother up here. This person has a shaded circle. I know it's a female because it's a circle. Shaded tells me that it's got attached ears, which tells me that the genotype is going to be lowercase e, lowercase e. We have the father, unattached ears, little dangly things like me. Okay, grandfather, if you like. In this generation here, we have female, 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 male. So there's 4 siblings, 3 girls, 1 boy. And when we look at them, we have unattached ears, attached ears, and attached ears. If we look here, we see that this particular male has had a union with this new female from outside of the family. And by being in the union with that new female from outside of the family has then produced a 3rd generation down here, 2 daughters, both of whom have got unattached ears. So what can we see? We don't know at the moment about the dad. We know that the mother right now is a homozygous recessive individual. So is generation 2, individual 2, generation 2, individual 4. They both are. Here we see this individual and this individual. They are both unattached. They've both received an allele from the mother. They've received an allele from the father. We know that the allele from the mother has to be lowercase e. So that's going to be one of the alleles. We know that they have the demonstration of unattached ears. Unattached ears is the dominant allele. So that tells us that this has to be a capital E there. So we have a heterozygous individual here. And for the same logic, this person has to be a heterozygous individual. Knowing that all of these young people have to get their lowercase e from the mother, because the mother can't give them anything else as an allele, that tells us that the father, who we know has a capital E present, that person, we have to think to ourselves, right, what is the genotype of that person? When we look at the genotype of this person here, the grandfather up here, we think to ourselves that we could have gotten the capital E dominant allele from the grandfather if he was heterozygous. We could have got the lowercase e recessive allele from the mother, since she's homozygous recessive. But when we look at this individual here, this individual has got 2 recessive alleles. Now, one of them is going to come from the mum, which means the other one has to come from the dad, which then tells us that this genotype simply cannot be an allele, or it cannot be a genotype for the grandfather. Generation 1, male, has to be heterozygous. Over in this region here, we know for a fact that these individuals are unattached earlobes. So they've got a dominant allele in their genotype. We know that their other allele had to come from the mother, and she's homozygous recessive. So that tells us that these 2 individuals are heterozygous. Okay, so here we see a pedigree chart. I've tried to draw a pedigree chart. I hope I've drawn it correctly. For someone who is, or for a family that has inside of their genetic code haemophilia, which is another thumbs up, which is a X-linked recessive trait. So haemophilia is an X-linked recessive trait. I've decided to show that the shading indicates those individuals who have haemophilia in this particular case. We have squares for males. We have circles for females. Okay, so let's go for the genomes that we definitely know. we know the genomes of the two males who are demonstrating haemophilia. So what are theirs going to be? They're going to be like this. So as you look at these three generations, generation 2, individual 3, generation 2, individual 3, they are a haemophiliac, and they have a trait. They only have one X chromosome, and so that X chromosome has to have the recessive allele on it. So that's a given. Okay. This person here, we have a, this person here has a son and 2 daughters. And what we can see here is this son is also a haemophiliac. This son here, being a haemophiliac, has received an X chromosome and a Y chromosome. Now we know that he got the Y chromosome from his father. So where did he get that X chromosome with the recessive allele on it? Had to get it from the mother. So what does that tell us about the mother's genome? At least one of the mother's XX chromosomes has to be carrying the recessive allele in order for this male to receive the recessive allele, because he gets the Y chromosome from the dad, which means he has to get that one from the mum. But we have 2 individuals here with XX chromosomes who are not haemophiliacs. So we know that these 2 individuals, both XX individuals, okay, we know these 2 individuals, they definitely have the capital H allele on at least one of their X chromosomes. This chromosome here has to be a lowercase allele from the father. So these 2 daughters down here, they get one X chromosome from the mother, one X chromosome from the father. The X chromosome from the father has to be the recessive allele, which means they're going to be heterozygous. These 2 are going to be carriers of the haemophilia condition. They will not be sufferers of the haemophilia condition, which is good for them. The son will be a sufferer of the haemophilia condition. He got that X chromosome with the recessive H allele from his mother. Finish off the mother's genotype. We have to see this X chromosome with the dominant allele had to come from the mother. So that's going to come from the mother. It is possible that these 2, our generation 2 couple, 3 and 4, it is possible that they could have a daughter who has haemophilia, but they have not. And that's where we say things are different between Punnett squares and pedigree charts. Punnett squares tell us what could be. Pedigree charts tell us what is for a particular family going back in time. Okay, what else can we get from this? We see here, this particular male, 2nd generation, individual 3, haemophiliac, got a Y chromosome from the dad. Got a Y chromosome from the dad. Got this X chromosome with the recessive H gene from the mother. So that tells us the mother, at the very least, has to have one X chromosome with the lowercase or the recessive allele. We see the mother has had daughters over here, and this daughter here has 2 X chromosomes, and this person is not suffering from haemophilia. So we know at least one of those chromosomes has to be capital H, and the other one, it could be capital or it could be lowercase. Coming from the father, we know the other X is a capital H because he is not a sufferer of haemophilia. This Y chromosome comes down here. That X chromosome with the dominant non-haemophiliac allele comes down here. And this particular chromosome could be either from the mother. Again, we see another male here. Dominant chromosome. Actually, yes, he's a dominant chromosome. Males are never going to be carriers of haemophilia because haemophilia is an X-linked. They are carriers, but they will always be sufferers as well as carriers. Whereas females, we see can be, we know that this female does not have the phenotype because we have not shaded this individual. So we've got a capital H there. Okay, so that's a bit on sex-linked pedigree charts. Don't forget I'm on direct messages. You can reach me anytime there. I hope this was of value to you. This is just the stuff that we covered in class today. We've got our assignment is due. The project is due on Monday, the 11th of March. We've got our checkpoint 2 being finished also on Monday, the 11th of March. Good luck to everyone, and I hope you're all well. See ya.